Okay. Good morning again. So our time together is short, and what we're going to do today is try to make the most of that time with not-flow homology, with some new memories in the time we have left. So what I want to focus on, sort of as we transition into talking about this, is some of the basic differences in the setup of this theory versus quantum homology we were talking about previously. And because we're not assuming a sort of a technical background on not-flow homology, I'm going to try to essentially be giving you a feel for the differences in the types of tools that get used and the perspectives that get used. Because while there are a lot of formal similarities, sort of when the rubber meets the road, the actual tools that you use in each setting sort of actually kind of are each theory going to its own corner and taking advantage of what's really special in it. So one thing I want to remind you guys of is I mentioned the first day, well, actually a couple of things. I'm going to probably interchangeably move between writing HFK and HFL. If you want to take one simple reason why we should think about wanting to look at links is that we're talking about cobordisms, then maybe if we want to think about cobordisms between knots, sort of we're thinking about something that's functorial and has composition law, we have to typically pass through things that are disconnected. So definitely want to be able to work with links. But I won't really mean anything different writing HFL versus HFK. And an important point that's going to affect everything that follows is that HFL requires pointed links. And what might at first seem to be a bit of a technicality turns out to be extremely central to the technical setup. So as a consequence, we'll need to fix components, on each component, at least one base point. You can have more than that if you want. And as a consequence, we're going to need decorated link cobordisms. So what should I picture as a decorated link cobordism? Well, I can start with this link cobordism, and then I know that I'm going to need some base points. And so I'm going to draw, for each one of these, a solid and a hollow base point. Or, sorry, not base point, but sorry, I'm conflating two different things, but you'll bear with me here. I need to have these doubly pointed data for the sake of the diagrams. And now I'll explain this more in a moment, but it turns out that if we're trying to think about, well, how well defined is the information once I've added base points, well, one thing you can do is imagine moving them around the knot and back to themselves. And if you aren't watching the whole time, you don't notice anything has happened. But maybe if you're watching closely, you might notice that in theory, you'll be getting some automorphism of your not-flow homology. And indeed, and I'll write down in a moment, you can. Actually, I guess I'll just write it down now. So Sarkar showed that the base point moving map can, and often does, induce a non-trivial automorphism of HFL. Okay. So if I drag them around back, that can, and often does, lead to non-trivial automorphisms. And so to have a theory which is going to have desirable functoriality properties, you're going to have to help track in a cobordism, especially, for example, sort of principally the trace of some automorphism. But in general, we're going to need somewhere to track what's happening with the base points. And so, for example, do I want to draw this in a particular way? I don't know. I'll just draw it. Not too interesting. Like maybe I'll put some genus here. Okay, so I may or may not have drawn sort of enough, but the point is what we're going to have is in addition to our base points, we're going to have our base points, and then we're going to have some dividing sets, or dividing curves, and they're going to separate our surface into what we're going to call a W region, or a W subsurface, and a Z region, or a Z subsurface. Okay, and these aren't going to figure prominently into the rest of the talk, but I just do want to have you keep in mind that whenever we talk about the cobordism, secretly we're always going to need to talk about decorating it if we want to assign some map to it. Yeah.
You say this, you need these pointed links. Is this because, is it when you want to understand the cobordism maps, or if you just want to define HFL about link, you also need them to be pointed?
So let's see if I can tell the difference. To have like good naturality and functoriality properties, you're going to need to track that extra data. Like if you don't, my understanding basically you need to work with like a rather severe quotient of your object by all the sort of possible geometrically realized automorphisms, because otherwise you have no well-defined way of comparing them. I think that's sort of the, at least one reason that you sort of need this data. But yeah, I don't know if this answers the question, but you
maybe just the follow up is like, but if you were dealing with one component links, right, then you wouldn't need these.
No, you still do. Yeah, you still do need your base points. That's right.
You would still
even for a knot. That's right.
Okay.
Yeah. Thanks. So even for a knot. Yeah. So I meant to draw a sort of schematic of this. So here, what I'm imagining is I have a base point P, and I take it for a ride around. Okay.
But then you still get a well-defined isomorphism class of the
Under which condition? Sorry.
I mean, if you mod out by automorphism,
Yes.
change the...
Yes, that's right. You do, but it's a sort of not your strongest possible object to work with, and is not going to sort of fit into as nice of a framework as we like. But absolutely, we would get and we'll see that in fact that essentially well, actually I guess we won't see it, but there are cases and arguments where that is in one sense or another the object that people have to work with in some context, or at least did. Okay, so part of the reason why I mentioned this is not just as technicality, but it turns out that understanding this particular automorphism is actually really central in working with these, especially for understanding link cobordisms. And it's also our first hint of what becomes a really important theme, which if there's sort of one thing I want the takeaway for today to be, it's that in practice, for studying link cobordisms using link floor homology, understanding the action on these link floor complexes by certain symmetries, whether they're geometrically induced or sort of algebraically sort of existing because of the structure of the theory, is sort of becomes the name of the game for working with these. Okay. So the I want to say history here. Yeah, so a little bit of brief background on setting up the cobordism maps here. We said that sort of Cavano homology was more or less sort of born to work with surfaces. It's sort of implicitly baked into the construction that you have this TQFT type structure. You still have to prove invariance and whatnot, but it's sort of part and parcel of the theory. In floor homology, it's not quite as immediate, at least especially not for the link floor setting. And a lot of the early naturality work was by Juhasz, various combinations of collaboration, Juhasz, Thurston, others. And then Juhasz and Marangon used structure floor homology for the actual forming manifolds, working with the exterior of a concordance to define concordance maps in link floor homology. And in particular, sort of introduce the idea of saying, if I have some slice disk, well, one thing I made a bit of a fib on the first day, really, in this theory, we're gonna have to, when we're working honestly with it, puncture our cobordism so we always have non-empty ends. So as some slice surface, I'll cut out a little unknot, a little disk surrounded by an unknot, and work with wrap from the unknot. And then, generally speaking, depending on your application, that's gonna, whatever your result being, invariant is going to be invariant of the original surface, because you can show that sort of not any sort of consequence of like some very minor automorphisms of cutting out a different ball, basically. But the idea of trying to say, let me do the most naive thing I can do to assign an invariant, which is take the knot homology of the unknot, which would just be a copy of our coefficient ring, map the generator forward, and I get some element in my knot homology of the boundary. That's what we might call a principal invariant of the cobordism. But then really building up to work of Zemke in, let's see, I believe technically 18, Zemke constructs sort of everything you would need here, constructs the full. One thing I should have mentioned, I believe here, if I'm not mistaken, my setup, this isn't really coming from an honest chain level construction. It's coming from something really on homology using superflow homology and I think using bypass, or not bypass, what do you call them? Yeah, okay. Well, anyway, the point is what Zemke does is sort of constructs what you would fully need at the chain level. And start to establish all the sort of naturality, pictoriality properties that you would need, as well as invariance. So it's a sort of a full 3+1 peak of t, or at least, and so as much of one as it can be, and also establishes invariance. So this was a bit of a fateful October. Actually, I guess this was 2016 now that I think about it. Yeah, and so in a span of, I think, 2 weeks, also papers by our fearless organizer, Charlie Shahi, Ayman Fikari, as well as a paper by another local, Lev Tapio, also gave constructions in other contexts, related contexts of cobordism maps. So this is something that was sort of, in the air of needing to be established. And I just want to point out, to conclude our little history background before we get into the meat, this is nicely exposed in Zemke's 700+ page thesis. I wouldn't wish reading that full thing on somebody. Actually, the introduction is particularly lovely. It has a sort of really nice discussion of TQFTs, at least in the Floor context, and yeah, it's really nice. Don't be daunted by the number of megabytes. Okay, so great. So I want to, before proceeding, what had been the question posed by Juhas and Marangon in this paper, which was basically, are there disks D prime in the 4-ball with the same boundary, such that they're what we might call their principal invariants, HF K of D of 1 not equal to HF K. Oh, this is all over hat. HF K of D prime of 1 are not equal. So there was this invariant sitting there, but no examples yet showing that it actually was an effective invariant. Okay. Where's the water? Okay, so before we start getting into now positive results in the background, I just want to pause if there's questions about the setup. So what did I say the main takeaway will be? It's that at every stage, really understanding the action of some operation on these complexes is really going to be what's essential. And part of the reason why this problem is hard is something we also saw a little bit in the Kovanov setting, which is, for one thing, this you're taking it sort of what is a straightforward construction. It's easy to define this because you don't have to make any choices. But now the problem is to distinguish it. You have to find some way of distinguishing what will we know by the arguments from the first day be non-trivial classes. You know, you're never gonna be like this one's 0 and this one's not. They're both non-zero. And we need some way to distinguish them, but we don't, especially without sort of good ways of identifying different descriptions of the boundary, we don't really have a way to naturally compare them. So one solution is to try to look for situations where you have some additional structure that you can put on the group that these are landing in. And so the first setting, right, so the problem here, the dilemma, is it's hard to directly distinguish So we had one fix for this in the Kovanov setting, which was because it was so concrete, we could flip the problem around and start with elements in the homology and then map them forward. And it's pretty easy to tell, integers or elements of the field apart. But here it's not as easy to write down or compute the maps for just arbitrary generators of this group. So the first examples where it was shown that you could distinguish slice disks using these. It was also due to Austin Simke, and they showed that yes, can distinguish certain deformed spun slice disks. So from the constructions course, you guys know all about the spun surfaces. And here, we're taking slice disks are sort of like half of a spun sphere. And what is deformed spinning in general going to be? Well, if I have some knot, actually, we draw the knot first. If I have some knot, and I think about fixing some ball that intersects it, then given some element phi in diffeomorphisms of S3 comma K, with phi fixing this little 3 ball. So for example, I always sort of have a hard time mentally picturing very many of these. One thing you can obviously do is just swing this around, right? Like, as you guys have seen multiple times, but just take a little cord. You can obviously do things like that, but you can also do something which would be to say, well, let me, for a moment, not fix the ball and drag it along, kind of like the base point pushing map, and then now just sort of think about pulling that back to actually fix the ball, and instead you're dragging the knot around, so you're swinging strands over and around until you come back to your original embedding. So for various types of automorphisms like this, we can get some slice disk for slice disks for K connectum minus K. Right? So I sort of take it and I sweep out my slice disk as I do that movement. Okay. So yes.
Are there any simple examples where the Charcot base point map induces like a trivial automorphism on HFL, or are there conditions under which we know that that's true?
Yeah, I think that in his paper he gives some like large classes of examples that you can sort of like simultaneously verify that they will have a non-trivial action. And there's a few ad hoc examples, and I'm almost positive that the ad hoc examples are negative examples, showing that there's not an interesting, I believe, but I have to double check. But I think that there are concrete known examples where it does not introduce it.
They're sort of sporadic, like there's no unifying property.
Not that I know of, but not really an expert in terms of the what's known about the base point moving map. But yeah, I believe that there's probably classes of examples you can construct, but yeah, I don't think that there's like some systematic understanding. Cool. Yeah, thanks. Yeah, great. So I want to say a bit more about this argument, not because it's what's the right way to put this, in a not rude way. You know, a lot of as they acknowledge in the paper, a lot of these, or all of these disks that they're looking at can already be distinguished using you know, topological tools. But as we sort of talked about, morally speaking, that doesn't mean that it's not worthwhile to understand how you can distinguish them with a more powerful invariant, because that same strategy might work in cases where topological tools fail. So the argument is going to feature a lot of the key properties, so it's a nice one to look at. And one of those key properties I forgot to mention right from the get-go, since I said I was going to compare h of k and kh, I meant to point out that h of l is defined for link cobordisms in arbitrary compact 40, well, I guess I don't need to say, I guess arbitrary 4D cobordisms between you know, exposed orientable pre-manifolds. So I'm no longer constrained to work with just things in S3 and the 4-ball or the product. You know, and maybe thinking about knotted surface knots in other pre-manifolds and other cobordisms isn't what gets you out of bed in the morning, but those can be useful for studying knots in the sort of classical setting. So, for example, what do? In this proof, they're going to identify, you guessed it, the action of this automorphism on h of k. There we go. And they're going to use that. Oh, sorry. I should write it this way. So the induced map on h of k. Okay. So what are they going to do? You're going to start with 2 copies of S3 and a copy of your knot and a copy of its mirror. It's a big personal victory every time I can actually draw the left-handed trefoil. And now what we're going to do is thicken these up. So now we just have these products. We have 2 little simple product cobordism or concordances from the knots to themselves. And now what I'm going to do is I'm going to attach a 4-dimensional one handle right along where a neighborhood of where these base points are. So this is some 4D one handle. And if I attach a 4D one handle to the upper boundary here are 2 copies of S3, I'm just going to end up getting a connect sum of S on the boundary. The effect is a connect sum of S3 with itself. So I'm going to get a cobordism from 2 copies of S3 to 1 copy of S3. And then inside there, if I think about this as being a interval across a 3 disk, then if I take the separating arc right across the middle of the 3 disk, or sorry, wait, 3 disk. Sorry, it's not gonna be separating. I've got this in two this. I just take sort of an arc from one into the other and having its boundary in the boundary. What I'm constructing is basically a pair of Kant's cobordism from K disjoint union negative K to K connect some negative K. Okay, so well, maybe I'll pause for 1 second just to make sure that the construction is clear. So I'm decidedly not you know, doing things now that I could do in quantum homology, at least not quite as naturally. I mean, this space ultimately will be standard, but it's expressed as a cobordism in this non-standard way. So great. So what we want to do now is consider the inverse cobordism. So negative x, that'll go from S3 to, well, I guess really sort of minus S3, but it's fine, to 2 copies. And minus sigma is going to go from minus K connect sum K to minus K disjoint union K. So this is going to induce, so F minus X minus sigma is going to introduce a map from HFK hat of negative K connect sum K to HFK of the disjoint union. And now we're going to get to do some fun trickery that just, again, uses some of these more formal properties. So let's try to think of what this thing is. For one thing, one of the basic principles or basic sort of computational facts about HFK is that this is going to be isomorphic to the, maybe I'll just write it here. That's not enough room. So that's isomorphic to the tensor product of the 2 factors. Okay, for starters. And then we know that mirroring is supposed to give us the dual. And then there's a natural identification of the dual tensor, the original space, that means this is just homomorphisms from, this is some vector space over F2. So this is going to be isomorphic to just homomorphisms from HFK hat of K to HFK hat of K. Sorry if that's too low on the board, but just everyone you can see, the bottom step has told us that this cobordism map is going to go from the connect sum to just homomorphisms from the one factor to itself, from K to itself. Okay. And they show that this is an isomorphism. Okay. And moreover, what do they show? They show that under this isomorphism, and this is sort of the key part, with the mantra of needing to understand actions of certain symmetries on the complex. They show that f of negative x negative sigma of HFK hat of if I define, I didn't give it a name, but if I define the slice disk associated to some homomorphism by dphi, then this principal, this thing we call the principal invariant, we show that this is none other than this in the homomorphisms of H of K. So the way to think about this is we're mapping into the H of K of this connect sum. The disk is giving us this sort of swinging around relationship between the right and left sides. And what we're saying is that actually you can sort of use this cobordism to unpack that and pull it apart. And what are you seeing? You're exactly seeing that the relationship between the left and the right side is basically a pairing, or a pairing, I guess it's the automorphism. That's precisely the effect of that automorphism on your not homology. Okay. So now that doesn't immediately prove this because you need examples where you can actually compute this. But we know what we do. So in particular, for example, if we do roll spinning, right? So that's like, base point moving would be if I dragged the ball around and came back. Roll spinning would be the associated thing if I kept the ball in place and dragged the knot to sort of reverse that. It turns out that roll spinning exactly induces the Sarkar base point moving map. So you automatically get lots of examples where d phi is not smoothly isotopic row boundary to the standard slice disk for K connect summits mirror. Okay, so one thing I want to point out is this is everything we're saying is really, unless otherwise noted, working over F2 coefficients, because that's where the sort of naturality properties and everything have been established, even though you can construct these theories over Z. Sarkar proves a key result, which shows that there's this other sort of naturally, floor theoretic definition of a map, not a sort of geometrically induced map, but a map induced by certain holomorphic curves, certain holomorphic curve count, and shows that, at least for knots in S3, the certain composition of these maps is equal to the base point moving map. So part of the technical work here is actually sort of identifying in more algebraic terms what that map is. If that result that he proves holds over Z instead of F2, then you can automatically get infinite families. But for the moment, this is just giving pairs because you only have sort of F2's worth. Okay. So, any questions about any of this discussion before we start to see where the story goes from here?
So does this thing not have to preserve the gradings in it?
Thank you. Yeah. So it's going to be a grading preserving automorphism. And you mean that you talk about the automorphisms, right?
Yeah.
Yeah, that's right. It will be. And also the cobordism maps themselves, right? In this case, while we're still considering, especially once you cut out a hole, the concordance, those will be grading preserving as well. And for cobordisms, we mentioned positive genus, we'll see a grading shift by whatever characteristic. And depending on the genus of the decorated subsurfaces. But anyway, but yeah, so the automorphism is graded. And
Both the gradings.
Yeah. Unless I'm squeezing up, I don't think it inverts them or something. Yeah, it should be because it should be effectively the action of an isotopy anyway. Yeah. Okay. Yeah. So good questions. Any other questions before we see what's next with this?
Do you expect that similar thing can be done for cobalt homology?
Yeah, it's a great question. I think that my understanding is that the most basic impasse is a lack of anything analogous to a Sarkar base point moving map calculation. I mean, in general, to understand when we look at K connect sum negative K and think about what this does, we're sort of dragging one component is sort of kind of equivalent to dragging one component along like the other one, like a roller coaster track or something. That, those maps are very hard to calculate in quantum homology because the computational complexity grows really fast. But I don't know. It's a good question. I don't know if anybody has any expectations or calculations. Yeah. So I do think that a lot of these things, there's a natural question of the counterparts in quantum homology. Okay, great. So next, well, it might seem slightly funny. So the next generation of obstructions that I want to mention is for anyone who's familiar with non-floor homology. Well, that's giving us some, in the case where you had some like F2 vector space, just intrinsically or maybe hard to study directly. If you can extract some numerical invariance, that's helpful. And for the same duo, Johaus and Zemke, in a paper later that year, they basically observed that the algebraic constructions that extract numerical invariance from H of K they have counterparts for surfaces. Okay, that's a lot of words. Not sure why I'm writing out all those words. But so, for example, the tau invariant, which we think about as basically saying I have some, but not one way to think about it is I still have a chain complex for the floor homology of S3 or whatever my ambient space is. The knot is inducing some filtration on it, and tau is basically going to ask about the minimal filtration at which the generator of the ambient space's floor homology sort of appears and persists. So you can do a similar thing for pairs of surfaces. You're basically asking, if I know that these maps are non-trivial, you can sort of show that eventually, sort of stably, they're going to be, not stably in the topological sense, but in the sense of the filtration, eventually they're going to be giving me the same element in the floor homology of the ambient space. And so you can ask the minimal filtration degree at which that occurs. And in general, constructions like tau, nu, okay, and this last one, oh, epsilon, that's okay, etc. Okay, so for these types of things, you can get invariance of surfaces, and they show that these give bounds on notions of distance between surfaces. So, for example, I could ask about, well, if I have some, maybe two surfaces, maybe they're not isotopic, but if they're sort of regularly, I can find some regular homotopy between them. I can ask what the minimal number of double points I need to have in order to pass between them. That's some kind of notion of like a singular distance, singularization distance or something. And the point that these give bounds on that, they also give bounds on the stabilization number, the number of times you need to add tubes to your surfaces to make them isotopic. And we'll chill out with talking about sort of elementary symmetries of knot diagrams, but I want to point out that they're never sort of far from view in this area. And in that paper, one of the other important technical steps that they develop are understanding the action of one of the types of quote-unquote summand swapping symmetries. So let's say I have one knot and another copy. So even though this is a connect-sum of the knot itself, I'm intentionally writing it in a way where I don't want the strong involution. I want the the map which takes it and rotates it by 180 in the plane and swaps the two factors. And that's actually not quite the end of the action, geometrically. You might notice that that's going to move this over here. And so after you do your 180, to actually get this back to an automorphism of your pointed link, you have to do a half base point push. Okay, so it's 180 composed with half gating twist. The base point. Okay. Now I want to point out there's another important type of summand swapping thing, which is if I instead had I guess I'll draw it this way. I can also consider this. This is another summand swapping symmetry. Okay, and understanding, for example, the action of this summand swapping symmetry is an important part of, for example, the 2-1 cable of figure 8 knot is not slice. This is part of factoring in the sort of the covering evolution on the branch double cover. So it really can't be overstated how central to a lot of applications understanding the action on polar complex of some symmetry is. And part of the reason why that is it gets away from this need to identify and work with concrete elements, because you can try to understand sort of abstractly how this is behaving. You don't need to sort of pinpoint the exact behavior on element by element. Okay. Okay, so before we move to sort of the even more modern set of techniques, let me pause and see if there's any questions about this so far.
Sorry, can you just describe the difference between those two again?
Yeah, so one way just like to quickly check that they're somehow different is this symmetry has no fixed points on the knot. Its axis of symmetry sticks out of the board, and we just like crank it like that. Whereas this has its axis of symmetry is in the board, and it's going to have 2 fixed points. And indeed, we want to put our base point at one of those. Yeah. So this is going to be some strong involution, whereas this is, I guess, just a free periodic symmetry. I don't mean free. I guess free. No fixed points. Yes. Yeah, thank you. Yeah, other questions? Good question. Okay. So, so far, what I've been describing are various ways of cooking up symmetries of certain connect sums of knots, some with its mirror, also not with its orientation reverse. And let's see what I want to say here. So I don't want to say too much about this, but it's important to not mention. We said one of the things that might be like a want to people who are not thinking optimistically is that, okay, well, a lot of these examples can be distinguished using basic topological tools. But again, the question isn't, what can, I don't know, what is it? Something like, don't ask what knot homology can do for your slice disks, ask what slice disks you can create for knot homology or something. I don't know. The point is, you need to think about trying to apply these tools to the right examples and hope that the computational techniques from the more elementary examples still bear fruit. And so, turns out that you can use link homology to detect infinite families of exotically knotted, sorry about that, exotically nodded. My son just learned to blow kisses, and now my family's group chat is like blowing up. I forgot to turn my notifications off. So exotically nodded slice surfaces. Here they're going to be of positive genus that'll be relevant. Greater than 0 in B4. And the way that they use these tools is not so immediate. The construction is going to use twisted rim surgery, which, I'll just say very, very roughly schematically, if we have some curve gamma in our surface, so the cartoon picture we're going to want to imagine is that we're basically going to tie some knot. It's definitely not going to be drawn right, but you'll forgive me. We're going to sort of essentially think about almost like spinning in a revolution into that cylinder. So they show that under certain situations, in fact, you need to technically work with the overall strategy is that they want to start with a non-vanishing result. Now, one of the non-vanishing results we saw was that for slice disks, they're going to induce non-trivial maps. That's because you can close them off with their upside down copy to get a sphere, and that's going to induce the identity on you as a concordance and a knot. Here, they want to work with surfaces of positive genus, and so the corresponding non-vanishing result they're going to use there is in fact that just like Amesca defines a invariant of braids in quantum homology, it's secretly it's invariant of transverse links in a contact structure, and there's corresponding invariant transverse invariant in knot-floor homology. And so they start off by showing that under a certain type of cohortism, for example, a type of quasi-positive braided surface, the transverse invariant is mapped non-trivially, and they also establish some sort of functoriality properties of it. And then they show that if you use sort of some souped up coefficients, you can detect the change coming from this. You're essentially going to pick up an action somewhere of the Alexander polynomial of the knot that you're using to tie this in. Okay, so some sort of different techniques going into that. And one thing I'll say out loud while I'm erasing, I forgot to say it before, part of what's underlying these bounds on distance between surfaces is really leveraging the torsion in knot-floor homology over adjoining U, so an extra variable. And just like we saw that you can use that in Kovanov homology or invariant homology briefly at the end yesterday, it's in fact way more useful in knot-floor homology because it's more abundant and it sort of behaves nicer under certain operations like cabling. Sort of the non-trivial torsion elements sort of proliferate under, for example, cabling in knot-floor homology. But as we sort of bring this closer to close, I want to mention the final sort of modern incarnation of studying a lot of these things. And so I want to just briefly define something more technical, in case people haven't seen it. But we're thinking a lot about symmetries, and if we have a complex with an involution on it, in particular, we'll define an iota complex. So what is an iota complex? It's a chain complex C boundary that's free, finitely generated over F adjoining U. And it has this involution iota such that C has a Z grading where the action of U lowers that grading by -2. So sort of formally, we're going to aim for something which looks like a knot-floor complex with sort of historically a certain involution in mind, but or a homotopy involution could be other types. And then where does this start to really appeal to some of those structural properties. Well, there's a map. Well, I think I want this to be an isomorphism to if I localize to F U inverse, and then iota preserves the grading, and up to chain homotopy, iota squares the identity. So it's a homotopy involution. So the two natural or central examples are geometrically we can think about this as being an honest involution induced by some symmetry, some actual symmetry than not. But historically, really the place where this is the techniques here are coming from are from involutive homology, where you have this sort of more structural algebraic symmetry of the theory. Okay, and so Hendricks Manilescu show how to extract numerical invariance of such a complex. And those invariants are nicely behaved under, if we continue the definition, the notion of local equivalence, which people haven't seen before, is a quite central tool now. So we'll say that a map from C0, or I guess C1, iota 1 to C2, iota 2, if these are iota complexes, then we'll say that it's a local map if it preserves the grading, it commutes with the involution, or I guess it intertwines, sorry, I should say intertwines, I think is the proper, intertwines the iotas and induces an isomorphism from U inverse. So we localize and to induce an isomorphism of the localized complexes. Okay, and so I'll wrap up in a moment or two, but just want to get to the sort of grand finale of these. So we say that that CI are locally equivalent if there exist local maps in both directions. I'm not saying that they have to be, inverse or anything like that, but just using local maps both directions. Okay. So there's various reasons one might try to do this, but if we again take the philosophy that working with the explicit groups, it's hard to study them directly. This is sort of singling out some coarse structure, and the invariants that you can extract of here are really local equivalence invariants, and for example, have nice behavior under different types of cobordisms. Okay, and so I think this is essentially the last thing I'll say out or on the board. So I think a 2020 paper, maybe it's a 2022 paper of Malik and Stoffergen. They use this to study, this and some other techniques, to study strongly invertible knots. Okay. And I'll just say, on the board, I'll say they get powerful isotopy equivariant slice genus bounds. What does that mean? If I say a slice genus bound, I just mean the minimum genus right of some smooth slice surface in the four-ball. If I say isotopy equivariant, well, if I have some knot with some symmetry, I can ask about surfaces over which up to isotopy that symmetry extends. So there's, if I'm working in the four-ball and I have some boundary, some symmetry in the boundary, I could say, is there for example, is there a disk such that if I look at K and tau of K, and I take some extension of tau over the four-ball, then is there an extension such that it takes the disk to the image under that symmetry? Okay. So what they show are, for example, that you can prove that this is strictly positive for lots of slice knots, including, for example, the mirror of 946 and that knot 17NH73, the one that mounts a pair of exotic disks. And so the upshot is that they're showing that there's no isotopic covariant surfaces. So that means if I have a slice disk at all, it cannot be rel boundary isotopic to its image under some extension of that symmetry. So without ever actually computing a four-dimensional cobordism map anywhere, these bounds are using sort of purely three-dimensional calculation to prove the difference between any such surfaces that would exist. And so if there's one slice disk, suddenly there's two, and they're not smooth isotopic rel boundary. Okay, so the final word I'll say about that is, as before, what you really need is a suite of techniques to reduce things to simple cases where you can do calculations. And so, for example, part of like the power of their work is that they showed that the numerical invariants they're extracting have nice behavior under sort of like certain types of crossing change cobordisms in like negative definite crossing change cobordisms. And also, they relate them to, and this is sort of, I guess, the final piece of the puzzle, something that quantum cannot directly do, which is relate the knot floor invariance to the invariance of the three manifolds obtained by surgery on the knots. And so you can start to leverage calculations of the three manifold invariance. So for example, if I have some concordance between two knots, I can do a surgery on that concordance and get a cobordism between some surgeries on those knots. And so you start to open up an entire avenue of obstructions that don't come directly from the TQFT itself, but through its sort of relationship to some other invariants. Okay, so I'll wrap up there. Thank you, guys.
Questions, Kyle?
In that picture of rim surgery, where does the gamma arc show up in the second picture?
So the way like that I drew this is a bit two-dimensionally reduced. What I should think about is if gamma is sitting on some surface, that surface is in four space. And so I can think about a neighborhood of gamma as being like an S1 cross B3. And so my surface right near there will always like cross, will always cross through like some sheet, and this annulus is the S1 cross that arc. And so you can sort of think about gamma as kind of being like that, but the basic point is, I mean, this picture is a bit of a cartoon, it's not totally honest, but the idea is that you're really going to replace this with some knot, and then do some movements around. So sort of gamma sort of kind of lives on as a point, for example, at one of the poles of the S1 cross one of the poles. Yeah. Yeah.